Hello and welcome back to another session on concepts. In this video, we will be talking about linear time invariant systems, and we will see what do we mean by linear time invariant systems or LTI systems. Before we begin the topic, I request all of you to please subscribe to the channel, like the channel, and share it with your friends so that it can have better reach. So let's dive into the topic. So what is an LTI system, a linear time invariant system? It is a system which satisfies two properties. The first property is called as a time invariance property, and the second is called as the linearity property. So any system that satisfies these two properties, that is time invariance and linearity, is called as a linear time invariant system. So let us first see what is time invariance. What do we mean by time invariance? So let us consider some system which has an input signal x of t applied to it, and the system produces some output signal y of t. Okay, and I am using the notation here for the signals in continuous time. The same ideas work even for the discrete time case as well. So an input signal x of t applied to the system produces an output signal y of t. So let's plot those signals. So let's say we have an input signal. For the sake of illustration, I'm going to consider an input signal which is like a rectangular pulse, okay, starting at time 0. And when we apply this input signal x of t, which is a rectangular pulse, let's say the shape of the output signal is a triangular pulse, like so. Okay, so this is our output signal y of t. Now, what do we mean by time invariance? In time invariant system, what happens is, if the input signal x of t is shifted by some amount, in this case, because it's a minus there, it means it is shifted to the right by some amount of time called tau, then the corresponding output y of t is also shifted by the same time amount in the same direction. So the input is shifted to the right by tau, so the output y of t is also shifted to the right by the same amount tau. So let's say the input, instead of starting at time t equal to 0, it is shifted to to the right by some amount tau. So that means previously the input was starting at 0, and now the input is starting at some amount of shift tau. So that means the input has been advanced into the future. So the corresponding output will also be advanced by the same amount of time. So the output y of t, which we had when the input was x of t, that will be shifted by an amount tau to the right. So we will have a shifted version of y of t like so. So what we notice is that when the input is shifted, the output also gets shifted. There is no other change in the output because of the shift in the output, shift in the input. So when the input has been shifted to the right by an amount tau, the corresponding output y of t is also shifted to the right by an amount tau. So this is also going to be starting at tau. So this is also, let me mark this. This is 0, this is 0, and this is 0. So when the input is advanced by a certain time, the corresponding output also gets advanced by the same amount of time. So this is what we call as time invariance. That means the system's behavior is not changing with time. When we give an input which is a rectangular pulse at time t equal to 0, we get a triangular pulse as an output. But when we give the same rectangular pulse at a later time, we get the same triangular pulse at a later time. This is what it means. Similarly, if the input has been shifted to the left by some amount, that means it is so let's say it is shifted to the left by some amount, and so let's say it is shifted to the left by some amount, and let's say if this is 0, then this is minus tau, right? Then the corresponding output will also be shifted to the left by some amount. So when input is x of t, we get y of t. When input is x of t plus tau, the output will also be y of t plus tau. That means the same y of t will be shifted to the left by some amount of time. So this triangular pulse will move to the left by a certain amount of time tau. So if you mark the time tau here, which is negative tau now, because we have the 0 here, so we will get a rectangular pulse which looks something like this as the output. So what we see is that for a time invariant system, a shift in the input produces a corresponding shift in the same direction and magnitude for the output as well. So this is the time invariance property. So the next property is called the linearity property. So let's see, what do we mean by linearity? There are two aspects to linearity. The first is called this the scaling factor. I will illustrate that with a few examples. So we call this as scaling. So for scaling, what happens is, let's say we apply an input x of t to the system and it produces some output y of t. Now what happens if the input is a scaled version of x of t? Let's say it is 2 times x of t. What would be the output of the system in that case? It will be a scaled version of the input of the output y of t. So 2 times x of t will produce 2 times y of t. So any scaling of the input produces a corresponding scaling of the output as well. So similarly, let's say the scaling factor was 1 by 3. Okay, so it's 1 by 3 x of t. Then the output will also be 1 by 3 y of t. Or in general, we can say that if a scaling factor a is multiplying the input x of t, then the output will also be scaled by that same scaling factor a. So the output will be a times y of t. So this is called as the scaling property. It is also called sometimes as the homogeneity property. Okay, so that's one aspect, the first aspect of linearity. The second aspect of linearity, so let me just partition this page so that there is no confusion here. So the second aspect of linearity is what is called as the additivity. So let's say we apply an input x1 of t and the system produces an output y1 of t. Okay, let's say there is a second input x2 of t and the system produces a different output for this input, which we will denote as y2 of t. Now what happens if the inputs are combined or added together? So let's say if the new input is the sum of x1 and x2, so that's x1 of t plus x2 of t, then what would be the output of the system? If the system is linear, then the output of the system in this case would be the sum of the individual outputs when x1 and x2 were applied. So it will be basically y1 of t plus y2 of t. So this is called as the additive property. When the inputs are being added or combined in some way, the corresponding outputs also get added or combined in the same specific way. So here the x1 and x2 are combined by adding them together. So therefore y1 and y2 are also combined by adding them together. Similarly, we can have scaled addition of x1 and x2. So let's say the input is now a1 x1 of t plus a2 x2 of t. What would be the output in this particular case? In this case, the outputs will also be a scaled addition of the corresponding outputs y1 and y2. So that means it will be a1 y1 of t plus a2 y2 of t. right? So a scaled combination, which we call as superposition of the inputs, produces a corresponding superposition of the outputs as well. So this is called as the additive or superposition property. Okay, so basically what we notice is that when the input is x1, we get an output y1. When the input is a1 x1, the output is a1 y1, which is the scaling property. So when it is scaled, when the input is scaled by some factor, the output is also scaled by the same factor. Then when we scale the second input by a factor a2, the second output is also scaled by the same factor a2. And when these scaled inputs are combined together by adding them together, a1 x1 plus a2 y2, then we have the output as a1 y1 plus a2 y2, which is a combination of the or addition of the scaled outputs as well. So basically this is combining the scaling property as well as the additive property together. We call this as the superposition property, and when a system satisfies these properties, it is said to be a linear system. So in general, what we say is a system is linear if both the linearity and time invariance properties are satisfied. And the importance of this LTI systems is that an LTI system is completely characterized by its impulse response. Now, what do we mean by impulse response? An impulse response is the response of the system when the input is a delta function. So when the input is delta of t, whatever output the system produces, we denote that by the notation h of t, and h of t is called as the impulse response. So an impulse response basically characterizes the all the properties of the LTI system. That means that if we know what is the impulse response of an LTI system, we can find out what would be the response of that system for any arbitrary input signal x of t. So the impulse response completely characterizes the LTI system, not just the output y of t, but we can also determine various properties of that system if we know what is the impulse response of the system. And the impulse response is nothing but the response produced by the system when the input is an impulse function. Again, what is an impulse function? This is something that we have seen earlier. An impulse function is having a value at time equal to t equal to 0 with a height of 1. So that's delta function, which is defined as delta of t equals 1 for t equals 0 and equals 0 for t not equal to 0. So this is the definition for the impulse function, and it's basically an impulse at time t equal to 0 with a height of 1. So if we know this impulse response h of t, we can calculate what is the output of the system for any arbitrary input x of t, and that relationship between the input, output and impulse response is given by the convolution between the input and impulse response equals the output of the system. So the output y of t of an LTI system is nothing but the convolution between the input x of t and the impulse response h of t. So the star here denotes the convolution operation. Again, convolution is something that we have seen in a different video already. So to sum it up, a system which satisfies linearity and time invariance properties is called as an LTI system. And if it is an LTI system, then it is completely characterized by its impulse response. That means if we know its impulse response, we know everything about the system. Okay, we can find out what is the output of the system for any arbitrary input by performing the calculation between that input and its impulse response, and that would give us the output of the LTI system. Furthermore, using the impulse response, we can also find out various properties of the system, like whether the system is stable or unstable, whether it is causal or non-causal, and so on. Okay, and we can also verify whether it is linear or non-linear. So the impulse response completely characterizes an LTI system. Okay, so that's to do with the LTI systems, and in general, we say that we can write this as an input x1 of t. So let's say it produces an output y1 of t. An input x2 of t produces an output y2 of t, and let's say we have a1 x1 of t plus a2 x2 of t. Then the corresponding output would be a1 y1 of t plus a2 y2 of t. And in general, okay, and this we will call as the output y of t of the system for a linear combination of the inputs. Okay, when the input signal of a system is a linear combination of some functions x1, x2, and so on, the output is also a linear combination of the individual outputs for each of those x1 and x2 and so on. So in general, rather than having just only two signals x1 and x2, if we have a1 x1 of t plus a2 x2 of t plus a3 x3 of t plus so on and so forth, then the corresponding output would be a1 y1 of t plus a2 y2 of t plus a3 y3 of t plus so on and so forth. So in general, we can write this as summation ak xk of t will produce an output ak, write the summation ak yk of t. So when the input x of t is a linear combination of some signals x1, x2, and so on, so k equal to 1 to, let's say, some n, then here also it's k equal to 1 to some n. So if we call this as our x of t, then this will be the corresponding y of t. Okay, so when the input is a linear combination of some signals x1, x2, x3, and so on, as a1 x1 plus a2 x2 plus a3 x3 and so on and so forth up to an xn of t, then the output y of t will also be a linear combination of the individual outputs y1, y2, y3, and so on. So that is a1 y1 plus a2 y2 plus a3 y3 and so on up to an yn of t. Okay, so that's to do with LTI systems, and this is what we mean by LTI systems. So a system that satisfies the linearity property and the time invariance property is said to be a linear time invariant system, and an LTI system is completely characterized by its impulse response. Okay, we'll stop here and we'll continue in the next video later.